I want to do one more example of finding the row or finding the rank in the nullity of a matrix. And then I also want to talk about that equivalency theorem that we've been adding to. So we'll get to that at the end of this video. So what I want to do is I want to explain how the determinant is relevant for finding the rank in the nullity. Big surprise, the determinant turns out to be relevant for basically everything that we're doing all semester. So what I want to do is let's take the determinant of A. And it turns out that what we get is -2. So you can check that what we get is -2. Probably the easiest way to compute the determinant would be to expand along the first column, and you get -2. In particular, what this means, and so let's kind of just deduce what this means and why this is going to be useful for us. What's the row reduced echelon form of A if the determinant of A is non-zero? Well, this tells us that the reduced row echelon form of A is going to be the identity. Okay, so that's going to be the identity. And what does that tell us? Well, that tells us that the rank of A is going to be 3. So this is a matrix, and the way that we're going to say this is that it has full rank, right? The rank is as big as it can be. The rank is 3. And if the rank is 3, and if the rank and the nullity have to add up to the number of columns, which happens to be 3, then that tells us that the nullity of A is 0. In other words, if we were to look at AX equals 0, the only solution that we would get would be X equals 0. And that's because X would be A inverse times 0, which is, of course, 0. So we get from the determinant being non-zero that the reduced row echelon form of our matrix is the identity. From that, we get the rank as being 3 and that the nullity of A is 0. So knowing the determinant of a square matrix can tell us something about its rank and its nullity. I want to be clear though, if the determinant of A is 0, all that tells us is that the rank is 0, 1, or 2. It doesn't tell us what the rank is completely. It just says it can't be 3. Okay, and the rank is going to be the number of pivots. So it could be 0, 1, 2, or 3. Okay, so let me write a few things down here. So if A is an n by n matrix, then the rank of A is going to be, how do I want to say this? The rank of A is going to be either 0, 1, 2, or n, okay, all the way up to n. So it can have any value from 0 to n, including 0 and n. The way that the matrix can have a rank of 0 is if it's all zeros, if there's no leading ones, if there's no pivots. So if you have a 0 matrix, that's the only matrix that has a rank of 0. And then the rest of those should be clear about how you can get the rank of a certain value. Now, if that's what we can say about the rank, then that also tells us a little bit about the nullity. The nullity of A can also be 0 through n. So I think at this point, let's put everything together in the equivalency theorem. So we had the equivalency theorem before, and that told us about the determinant being non-zero and having an inverse and all these things. But we can say a little bit more now. Okay, so the equivalency theorem. So the following are equivalent. Okay, so the following are equivalent. One is, and let me add for an n by n matrix, n by n matrix A, the following are equivalent. Okay, so just to be clear that we're talking about an n by n square matrix. One is that A has an inverse. A is non-singular, is maybe the way I should write that. That's what I was going to write at first. A is non-singular. Okay, remember that just means the A inverse exists. Okay, that's equivalent to saying that the determinant of A is not 0. that's equivalent to saying that the reduced row echelon form of A is the n by n identity. That's equivalent to saying that A is the product of elementary matrices. So A is a product of elementary matrices. That's equivalent to saying that AX equals B has a unique solution, right? That follows from knowing that A has an inverse. In particular, AX equals 0 has only the trivial solution. And that's when X is equal to 0. And up to this point has been old news, right? These are all things that we should know up to this point. This is I think the content of the first version of this equivalency theorem. But I'll call this version 2. Okay, this is kind of the revision of the equivalency theorem to incorporate new ideas that we've talked about. And then we'll be able to say a little bit more at the end of the semester about more and more terms that we're adding to this equivalency theorem. So let's add a few things here. A is non-singular. In other words, A inverse exists if and only if the determinant of A is non-zero, if and only if everything else. The reduced row echelon form of A is the identity. This is equivalent by what we saw up above to saying that the rank of A is n, or that's also equivalent to saying that the nullity of A is 0. And then I just want to think about what are those two items going to tell us. If the rank of A is n, the rank is the dimension of the row space or the column space, and that tells us that the rows or columns span Rn, depending on whether you're thinking of Rn as a set of column vectors or row vectors. But also this tells us that the rows and columns of A, let me write this just a little bit better. And in fact, let's make this two items. So the rows of A span Rn, the columns of A span Rn. Okay. That's also equivalent to saying that the rows of A are linearly independent. Or that the columns of A are linearly independent. Okay, and those are all equivalent to saying that A has a non-zero determinant, right? So again, somehow this determinant encodes a whole lot of information about the matrix A, information about whether it has an inverse, whether or not AX equals B has a unique solution, whether A is a product of elementary matrices, what's the reduced row echelon form of A, what's the rank of A, nullity of A, row space, column space, whether those rows or columns are linearly independent, and more. More is to come. So the determinant, again, holds a lot of this information. One last thing I want to say about this theorem, when I call it the equivalency theorem, what I mean is that all of these statements are equivalent in the sense that either they're all true or they're all false. So if you know any one of these things, if you know, for example, that the determinant of A, so let's just look here. If you know that the determinant of a matrix is non-zero, that tells you everything else about that matrix A. It tells you that A has an inverse, that A is the product of elementary matrices, that the rank of A is n, and so on. So that's what I mean when I say equivalent, is that if you know any one of these, then that tells you everything else. On the other hand, if you know that the determinant of A is 0, if you know that A does not have an inverse, that also tells you that the rank of A is not n. The rows do not span Rn, and so on. Okay, so when I say equivalency, I mean that all of these have the same truth value. Either they're all true or they're all false. Knowing the truth value of one of them tells you the truth value of the rest. Okay, so that's version 2 of the equivalency theorem.